The paper we're diving into today is Low-Cost Experiment to the Correct Relativistic Energy Formula by David Lush. Bit of a mouthful, but honestly, the questions it raises are pretty fascinating.
Yeah, this one really made me sit up. Basically, Lush asks, hey, what if the formula we all use for relativistic energy, Einstein's famous E equals mc squared thing, isn't actually the most fundamental version? Like, what if there's another valid formula that works just as well, or maybe better in certain contexts?
Right. And in this paper, Lush compares Einstein's version with an alternative that's been proposed by Osiak. So the big question he's trying to settle is, which relativistic energy equation actually reflects physical reality? I mean, no big deal. Just trying to overturn 100 years of physics.
Yeah, small potatoes. But seriously, the significance here is huge, right? This basically gets right to the foundation of modern physics. If our main energy equation is off, even slightly, it might ripple out into how we understand everything from particle physics to cosmology. Stuff like dark energy, inflation, even dark matter.
Exactly. The alternative formula comes from Osiak's idea, which is built not from Einstein's 3D Planck equation, but from integrating the Minkowski equation. The four-dimensional approach. And Osiak's version actually gives a rest energy that's half of Einstein's. So instead of E0 mc squared, you get E0 equals mc squared over 2.
Yeah, and for moving particles, the formula is even more wild. It becomes E equals gamma squared mc squared over 2. So it's quadratic in the Lorentz factor gamma, not linear like the standard E equals gamma mc squared.
Here's a quirky thing, though. Osiak's formula lets gamma, the Lorentz factor, be negative, without invoking any of those weird negative energy states that give physicists nightmares. That opens up whole new interpretations for antimatter and time symmetry.
Which is kind of trippy. But Lush points out there's a downside to Osiak's approach. It doesn't conserve energy in relativistic particle collisions. Apparently, that's the main reason Einstein's version became standard. It's the only one that keeps energy conserved when things are moving really fast.
True, but Lush argues that energy non-conservation might actually be a feature, not a bug. He ties it into all these weird cosmological observations, like why the universe is expanding faster than expected, or why dark energy might exist at all.
I liked how the paper keeps circling back to experiments. Lush proposes a clever, low-cost experiment using standard pair creation, shooting gamma rays at heavy nuclei to create electron-positron pairs. The idea is to check if the positron literally appears after the event, as standard theory predicts, or if it could be detected before, according to Osiak's framework.
The thing that jumped out at me, if Osiak's right, positrons, which are like time-reversed electrons, might actually be detectable before they're created in the lab frame. That's wild. Like actually probing the nature of time with a particle detector.
Yeah, it starts getting into that realm where physics feels more like science fiction. But Lush provides practical tests. Look for time advances in positron detection, compare trajectories in magnetic fields, actual empirical ways to distinguish between theories.
And he brings up this whole thing about how changing the energy formula might explain the missing mass in galactic rotation curves, classic dark matter problem, without needing some new particle. If you double the energy in certain collisions, you might account for that extra gravity.
Right, though, I have to admit, there's a part of me that gets suspicious here. Like, physics is full of people dreaming up alternative models that try to explain away dark matter or dark energy.
Yeah, totally. And honestly, not all of them hold up when the data comes in. But I think Lush's point is less about saying Einstein is wrong, and more that science should keep pushing at the boundaries and not rule out alternatives just because they don't fit the current narrative.
There's also this side digression in the paper about preons, remember? Like, what if quarks and leptons are made of even smaller bits? It doesn't totally flow with the energy experiments, but I guess it's all part of asking, What's really fundamental?
Yeah, I kind of lost the thread there for a minute. But the upshot of the whole paper is, let's not treat equations as gospel. Physics progresses when we're open to experiments that could shake the bedrock. I mean, we might not end up upending E equals mc squared, but even asking the question can tell us a lot.
Couldn't agree more. Even if this alternative formula doesn't pan out, trying to prove, or disprove, it pushes the precision of what we know.
The paper we're diving into today is On Einstein-Minkowski-Osiak Relativity by David Lush.
Okay, that's quite a title, right? I feel like just saying it out loud almost makes me smarter. But yeah, so this paper by David Lush is basically revisiting, well, challenging actually, some of the key ideas we all thought were settled in relativity.
The core question is, honestly, a wild one. What if the textbook version of Einstein's relativity isn't the only game in town? Lush explores an alternative called Osiak relativity that's based on different mathematical assumptions. Specifically, it argues that if you base your descriptions of particle mechanics on fully Lorentz-invariant Minkowski equations, so four-dimensional equations, rather than the usual three-dimensional Planck ones, you actually get different formulas for energy.
And it's not just some subtle difference. It literally changes what the rest energy, kinetic energy, and total energy of a particle are supposed to be. Apparently, in this Osiak version, the rest energy is E0 equals mc squared by 2, instead of the classic E0 equals mc squared.
Yeah, which, if you love your Einstein posters and mugs, kind of hurts, right? I mean, E equals mc squared is like the most famous equation in physics.
I know! But the significant thing here is, Osiak relativity doesn't conserve energy in relativistic collisions the way Einstein's version does. Instead, it preserves something called the temporal component of 4 momentum. So, for all practical purposes, like the energy thresholds that smash particles together, they still come out right, but the underlying principle isn't energy conservation, it's temporal momentum conservation.
That is a lot to wrap your head around. I love that nerdy distinction, though. It's a reminder that the universe doesn't care about what's in our textbooks. But back up. Does this mean all the observed conservation laws are just aspects of momentum conservation in this framework?
Pretty much, yeah. If Osiak relativity accurately describes nature, then what we've been observing and calling energy conservation is actually a reflection of 4 momentum conservation. Which, honestly, makes me a little dizzy, but...
No, same. Because that's like saying all of these collision experiments we've done, all of physics built on those, maybe our explanation's been wrong, even if our calculations lined up. It's very, you've been using the right recipe, but you don't understand why it works.
Exactly. And Lush really stresses that this isn't just theory for theory's sake. Like, he mentions possible consequences for dark energy and dark matter. That if energy isn't strictly conserved, maybe that missing energy we attribute to dark energy or dark matter is just, the universe not keeping the kind of books we expected.
I mean, it would be kind of poetic if dark energy was just the universe bungling its accounting.
Or being way more clever than our equations. Oh, also, this is a fun side note, and then I promise we'll get back on track. Lush goes off about how, under Osiak relativity, the electromagnetic field should be complex valued, not just real, which could maybe connect to why quantum mechanics uses complex numbers everywhere.
Yeah, that's wild. Like, maybe the math weirdness in quantum stuff isn't just quantum is spooky. Maybe it's just our relativity being incomplete.
And to make it even more spicy, Osiak relativity resolves some persistent puzzles, like the spin-orbit coupling anomaly in atomic physics. In this new framework, the energy levels just make sense without introducing things like Thomas precession, which always felt kind of like a fudge to me.
This brings up a meta point, actually. One thing I keep coming back to, reading through this paper, is how scientific theories aren't absolute truths. They're frameworks. And sometimes we find out the framework we've been using is kind of off. But if it still made good predictions, should we care? Or should we push for something more fundamental, whatever that means?
Yeah. Like, does it matter if it's momentum or energy being conserved, as long as a collider produces the right amount of stuff? Maybe it only matters when we want to explain something that doesn't fit, like dark energy.
And honestly, listeners, that's the kind of philosophical rabbit hole academic research leads us down. Lush isn't claiming he's found the truth, but he's showing that there's more to explore. And sometimes that means turning long-cherished ideas on their heads.
If anything, it's a good reminder not to take textbook physics as unchanging gospel. The real universe might still have surprises up its sleeve, just waiting for someone to reconsider what everyone else took for granted.
Absolutely. The paper we're diving into today is Quantum Wave Mechanics as the Magnetic Interaction of Dirac Part by David C. Lush. It's a mouthful, I know, but stick with us. This one's actually trying to answer one of the deepest questions in physics. How is quantum mechanics connected to classical physics, specifically through the magnetic interactions of spinning particles like electrons?
Yeah, so the central problem here is all about the quantum wave function, right? That mysterious thing in quantum mechanics that tells us where particles might be. Lush asks, could this wave function actually emerge from just classical, relativistic electromagnetic interactions between particles if you model them with internal circulatory motion, the so-called Zitterbewegung or Zitter model?
Right. So instead of the wave function being this mysterious, standalone thing, he's looking at whether you can get something that looks and acts like the Schrödinger wave function, pretty much the core object in quantum mechanics, just from considering electrons as tiny charges spinning really fast, at nearly the speed of light.
It's worth pausing on why that's a big deal. If you could show that all that weird quantum behavior, like particles being in two places at once or quantum tunneling, if that just pops out of good old classical physics with a tweak, it would change the way we think about reality. It doesn't solve everything, but it maybe demystifies a lot of quantum theory.
Exactly. So what Lush does is he looks at the force between two of these Zitter particles. Think of electrons as tiny spinning tops, but moving so fast they're practically at light speed. When you include the magnetic interaction between them and make things time-symmetric, meaning you include advanced and retarded electromagnetic interactions, a bit like Wheeler-Feynman's absorber theory, a new pattern emerges.
The core finding here is really cool. The magnetic force between these two spinning charges is modulated, meaning it oscillates, in a way that's mathematically very similar to the quantum mechanical wave function. It solves an equation that's almost the same as the Schrödinger equation, although in the standard relativity, it's almost because of a factor of 2 difference.
But here's where it gets twisty. Lush introduces a modified version of relativity from Osiak, where the relationship between mass and energy is E equals mc squared over 2, not the usual mc squared. When you use that, the modulation matches the Schrödinger equation exactly, with no extra factors.
I mean, that's pretty wild. If this alternate relativity is correct, which is, a big if, then quantum mechanics, or at least its central wave equation, might actually just be a feature of classical physics with this Zitter model. And to be fair, that's far from universally accepted, but it's an interesting proposal.
And let's not forget, he brings in the Wheeler-Feynman absorber theory to help explain how particles can have time-symmetric interactions. It's a bit mind-bending. Advanced waves, retarded waves, the idea that absorbers in the future and past play a role in what happens now. Sometimes it almost sounds like science fiction, but it's tied to real equations.
Absolutely. The upshot is that, under this framework, the wave function isn't some mystical cloud, but a manifestation of synchronized, or sometimes desynchronized, internal motions of spinning particles, communicating with each other via classical electromagnetic forces. It recasts quantum probabilities in terms of these phase differences between spinning particles.
There's nuance, of course. For example, Lush points out this only seems to work perfectly for particles with aligned spins and equal mass, which doesn't always fit the messy reality of protons, electrons, and composite particles. He speculates about deeper structures, preons inside electrons and quarks, which, honestly, is a whole other rabbit hole.
Yeah, and he admits there are still open questions, like how this framework handles cases where spins aren't aligned or particles don't have equal mass. He suggests that some modifications, like those preon models or more complex absorber behavior, might fill the gaps. But it's very much work in progress.
In the end, the real takeaway is that quantum mechanics might not be as mysterious or as fundamentally other as we sometimes think. Academic research like this doesn't settle things, but it gives us fresh ways to connect ideas and see where classical and quantum blur.
Exactly. Whether or not Osiak's relativity is right, or if every electron is really a bundle of jittery charges, the beauty here is that science keeps digging deeper, asking, could we make sense of the universe with the tools we already have, if only we look at them differently?
The paper we're diving into today is Does Bohm's Quantum Force Have a Classical Origin? By David Lush. I have to say, this one had my mind buzzing from the very first paragraph.
Yeah, same. So the central problem Lush is poking at is deceptively simple on the surface, but really goes to the heart of quantum mechanics. The question is, could that so-called quantum force in Bohmian mechanics, that weird thing that cancels out the attraction between the electron and the proton in a hydrogen atom, actually be explained using classical physics? More specifically, could it be a magnetic force we've somehow overlooked?
Right. I mean, that's a pretty radical question because, quantum forces are usually considered distinct from anything classical. But Lush is like, wait, maybe if we look at electrons as these little charges zipping around in a tight circle at the speed of light, a motion called Zitterbewegung, maybe their classical electromagnetic fields do something really interesting.
That's the Zitterbewegung idea from Dirac's early work, right? The notion that instead of sitting perfectly still, an electron's charge is actually moving in a crazy fast circle, which gives rise to all sorts of quantum properties, like intrinsic spin.
Exactly. What's wild is that Lush points out if you actually calculate the magnetic force between two particles with this sort of motion, you get a term that, in the far field, like when the particles are not right on top of each other, falls off as an inverse square law, just like the regular Coulomb force. But here's the kicker. Under certain circumstances, that magnetic force can be equal in magnitude, but opposite in direction to the regular electrostatic attraction between the electron and the proton.
So let me get this straight. If two electrons, or an electron and a positron for that matter, both have this internal zitter motion, and those motions are aligned but, say, half a cycle out of phase, then the magnetic part actually cancels the regular electric attraction?
Yeah, Lush lays out the math. Although, full disclosure, the equations are a bit of a forest, but the upshot is really clear. It basically means if you're using this model, you could, in principle, recreate the quantum force that keeps the ground state of hydrogen stable, but only using electromagnetic forces that come purely from classical physics.
What I found super interesting was that the paper doesn't stop there. It also discusses how this modulation in the magnetic force, the way it oscillates depending on how the two cycles line up, analy, has a spatial period equal to the electron's de Broglie wavelength at low velocities. That just feels so spooky. Like, you take something that seems utterly quantum, and it emerges naturally from classical relativity if you add this twist.
But there's a really important caveat. This isn't a slam dunk answer or a grand unification. For one thing, the magnetic force can actually flip direction really rapidly, over distances smaller than the width of an atom. So while it matches the quantum force on average, At tiny scales, it's all over the place.
Which sort of helps explain, I guess, why it's not obvious in more naive classical models. It's a highly hidden effect. Also, and Lush stresses this, quantum mechanics isn't wrong just because we can give classical analogs. Research like this gives us more tools for thinking about why quantum stuff is so weird. It doesn't mean we should start throwing out Schrodinger's equation or anything like that.
Exactly. And I really appreciated that the paper calls out its limits. Like, it mostly works for equal mass particles, so it's more suited to positronium than actual hydrogen atoms. Plus, the idea hinges on whether nature actually allows advanced electromagnetic interactions, not just the usual retarded ones, which is still, well, open for debate.
You know, that whole advanced versus retarded interaction thing always makes me think of science fiction, like time travel or signals going backward. I once read somewhere you could make a weird radio that hears your favorite song before it's even played. Obviously doesn't work like that, though. Anyway, probably off topic.
Ha! I'd love to see that. But yeah, so going back, if a listener's wondering, does this mean quantum weirdness is finally solved? No, not really. But it does mean some of the strangeness we see in quantum mechanics might have echoes or shadows in classical physics that we haven't fully explored or understood. It kind of broadens the conversation.
Agreed.
The paper we're diving into today is Dirac Quantum Theory Using Alternative Relativity by David Lush. It's quite a dense read, but wow, there's a lot in there to unpack.
Yeah, I have to admit, when I first saw that title, I thought, here we go. Someone's ruffling the feathers of physics again. But, it's actually addressing something pretty fundamental. How we reconcile quantum theory, especially the Dirac equation for electrons, with an alternative form of relativity, not the one we're all used to from Einstein.
Yeah, exactly. The core question Lush is digging into is, what does it mean for quantum theory, particularly Dirac's framework, if we adopt Osiak's alternative relativity, rather than sticking to textbook Einsteinian special relativity?
And right there, that's a big deal, because Einstein's relativity underpins so much of both classical and quantum physics. But Osiak's version gets kinetic energy from integrating the Minkowski equation of motion, so a fundamentally four-dimensional Lorentz invariant equation, instead of the usual Planck force equation that's only three-dimensional. That sounds subtle, but it totally shifts how energy is calculated.
The headline is that, according to Osiak relativity, the energy of a free particle is halved. Like, for a resting particle, its famous E equals mc squared energy becomes just mc squared over tav. Lush shows this doesn't break Dirac's theory for a free electron. In fact, it sheds new light on things like antimatter and the way matter and antimatter pairs get created and annihilated.
I liked that discussion about negative energy states in Dirac's theory, too. Traditionally, those negative energies get interpreted as antiparticles, like positrons, traveling backward in time. That's wild enough, but in Osiak's setup, those states have positive energy, but the temporal part of their form momentum is negative instead.
That's such a twist, right? We usually equate the temporal part of form momentum with energy. Osiak says, no, they're separate. The temporal form momentum stays the same as in Einstein's version, so the rules for things like particle creation thresholds still work. But what we actually call energy just isn't the same thing anymore.
And, honestly, that brings up sticky questions for conservation laws, which we've always considered almost sacred. In Osiak relativity, energy can be non-conserved, especially in highly relativistic collisions. But form momentum is still always conserved. It might sound like theoretical hair-splitting, but Lush argues that this could actually help explain puzzling phenomena like dark energy or even cosmic inflation.
It sort of flips the script. People worry about energy non-conservation, but maybe, in some extreme conditions, that's the missing ingredient we need. There's even a proposal that the so-called missing energy fuels universal expansion.
And there's this bit about photon energy, which sort of, tripped me up for a second. In Osiak's setup, a photon's energy is h nu over 2 instead of h nu. And that fits better with some old arguments about the standing waves in the blackbody radiation problem.
The way he links that to de Broglie waves is clever too. If you have the rest energy but use the electron's spin, since electrons have half the spin of a photon, you end up preserving relationships between frequency, energy, and momentum. It keeps the mathematics of Dirac's theory intact, but the interpretation is well, you have to change your mindset about what's real.
And if you're listening, you might be asking, does any of this matter, or is it just mathematical games? Lush argues there could be experimental tests, like in pair creation events. He claims that if you could watch carefully enough, Osiak's relativity predicts the positron, the antimatter electron, should be detectable before the pair event, annihilating before it's even created. It almost feels like a physics prank, but that's what his equations say.
Right, so in principle, the difference between Osiak's and Einstein's relativity could be tested, at least if our particle detectors get fast and precise enough. You know, sometimes I wonder if, in 100 years, people will look back and see debates like this as the real groundwork for how we explain dark matter and dark energy.
I doubt I'll be around to see it, but yeah, maybe. Of course, the idea that all these conservation laws, like energy, are only true under some definitions is a little unsettling. Reminds me of when we learned that, Pluto wasn't a planet anymore. The definitions change, but the physics, well, the phenomena, are still there regardless.
That's such a great analogy. Science keeps evolving, and sometimes what we take as foundational is just the best story for now. The paper we're diving into today is Spin-Spin Coupling as the Origin of Atomic Binding by David Lush. I gotta say, this one's a bit of a brain bender, but it really challenges the way we typically think about atoms holding together.
For sure. So, right off the bat, Lush is taking on this core question. What actually binds electrons to atomic nuclei? We usually think about the Coulomb force, that good old attraction between positive and negative charges, as the glue in atomic structure.
Exactly. But Lush digs into this alternative, almost radical idea. He's kind of poking at the holes in the standard story, especially when you look at things through the lens of quantum theory, de Broglie-Bohm specifically.
Yeah, he points out that in Bohm's version, for atomic states, this so-called quantum force actually cancels out the Coulomb force mathematically. That's pretty wild, right? If the very force we usually rely on cancels, something else has got to be doing the job of keeping atoms from flying apart.
That's the crux of it. The big claim is that magnetic interactions, specifically spin-spin coupling from charges moving at relativistic speeds, could be responsible for atomic binding. So essentially, it's not just static charges pulling on each other, but their intrinsic spins. Think of them spinning, almost like little tops, creating magnetic forces that act kind of like the Coulomb force.
And Lush leans on this Zitterbewegung concept. You ever heard that term before this? It's this jittery motion predicted by the Dirac equation, where instead of picturing an electron as sitting still, or even just orbiting the nucleus, it's kind of zipping in a crazy, almost light-speed little circle.
Right. And if you model electrons and similar particles as these zitter particles, you get these highly dynamic internal motions. The wild thing is, these motions generate their own magnetic fields, and the theory shows that, under certain conditions, the resulting magnetic force between two such particles can have the same form as the Coulomb attraction. So, a 1/r² radial force, just like what you see with electric charges, except it comes from these internal spins.
But there's a twist. The strength and sign of this magnetic force depends on the relative phases of the two particles' spins. In some cases, it can modulate, that is, it oscillates depending on how the two particles' internal jitters line up over space and time.
Yeah, and the really cool connection is that this modulation ties directly to the de Broglie wavelength, the wavelength associated with quantum matter waves. So Lush is making this bridge. He's saying the very quantum properties we normally interpret probabilistically could stem from concrete, classical spin-spin effects.
The methods are pretty deep in the weeds, mathematically speaking. There's a lot about retarded and advanced electromagnetic potentials. Lush argues that if you treat the electromagnetic interaction as time-symmetric, considering not just signals propagating forward, but also backward in time, you end up with some very strange but potentially significant consequences.
There's a subtle point there. Advanced fields are not something we experience in daily life. You don't, receive a light signal before someone sends it. But at really tiny scales, in the math, these advanced effects could, in theory, cancel out the ordinary Coulomb force we always talk about.
Which could be why, in Bohm's quantum picture, the usual glue goes missing, and something else, a spin-based magnetic glue, has to take over. But hey, this brings up a digression. Doesn't this make you wonder if, like, the macroscopic symmetries we see, like time only going forward, are just a quirk of scale or statistics? Quantum mechanics is always hinting at a much weirder universe.
Yeah, sometimes I wish my coffee would arrive before I order it, but, causality has its limits. Back on track, though, there are some objections, and Lush is upfront about them. For one, this only works if particles have parallel spins, and only if their masses match. So, not a perfect explanation for every atom.
Plus, there's little observational evidence for these advanced fields, or for this Zitterbewegung, being a physical reality. It's more of a theoretical playground, for now anyway.
True. But even so, the implications are interesting. If this mechanism plays any role at all, it suggests atomic structure might be more about deep, dynamic symmetries, spin, time reversal, and motion, than about static charges. It's a reminder that science isn't about finding one absolute truth, but about exploring new ways of seeing familiar things.
Exactly.
The paper we're diving into today is The Magnetic Force as a Kinematical Consequence of the Thomas Precession by David C. Lush. Quite a mouthful, right?
Yeah, I had to read that title a couple times before it started making sense to me. But it's actually asking a really big question. Could the magnetic force, like the same kind of force we see in everyday magnets, just be a kind of side effect from the weird way space and time behave when things move really fast? Especially when you bring in something called the Thomas precession.
Exactly. And just for anyone who maybe hasn't thought about Thomas precession since physics class, or, ever, it's this rotational effect you get when a particle moves and accelerates at relativistic speeds, meaning near the speed of light. Basically, it makes the reference frames of moving particles rotate relative to each other.
And that's super fundamental. Lush's core argument is, what if the magnetic force, instead of being just one piece of Maxwell's equations, a kind of force on its own, is what you'd expect to pop up just from this kinematic twisting, this Thomas precession, as you switch reference frames?
Right. The significance here, and why I think it's actually pretty bold, is that it tries to demystify magnetism even further. Instead of electric and magnetic fields are two sides of the same coin, which is standard relativity, it goes, hey, maybe the magnetic force is what you have to see if you're tracking with all the correct frame rotations as charges get pushed around. It's like he's saying magnetism isn't its own thing. It's just the price of doing kinematics correctly in relativity.
So to unpack the main method a bit, Lush considers two classical charged particles, one acting as a source and not accelerating, like it's super heavy or maybe it's part of a wire so it can't move. The other's getting flung around by the electric field, the Coulomb force. He's walking through, like, what does the observer who rides along with this test particle see? From her perspective, reference frames are precessing, twisting around, all because of the Thomas effect.
And what's wild is that when you tally up all the pseudo-forces she expects, Coriolis, centrifugal, Euler, like the kinds you get on a spinning merry-go-round, some are there, some aren't. Specifically, there's no Coriolis force in the source particle's rest frame, because from that particle's point of view, nothing's turning. This means, though, that an anti-Coriolis force has to be popping up somewhere, almost as compensation. And that's what, in the usual inertial frame, looks exactly like the magnetic force. Seriously, that connection feels so satisfying. Like, you almost want to high-five relativity.
I know! And it's not just a formal analogy. In his equations, the magnetic force in the lab frame is identical to this missing or anti-Coriolis force viewed from that precessing test particle frame. You can see the math. He even gets the mass dependence to drop out, just like the real magnetic force, which only cares about the velocity and the charges.
And, he doesn't stop there. He teases out, okay, if the Coriolis term gives you magnetism, what about centrifugal and Euler terms? Could they hint at the origins of the strong and weak nuclear forces? I mean, that's a hefty leap, but his argument is that at really high energies, like inside an atomic nucleus, there might be a Thomas precession-induced anti-centrifugal force that could be, well, strong and always attractive. He goes as far as to do some quick calculations, comparing how it might stack up to the size of a nucleon. Spoiler, it's a bit too weak, but not wildly off.
He does admit that this isn't the last word, like it's just a start. There are things he hasn't calculated, like the effects of field retardation, so it's not perfect. But, the idea that maybe the deep forces of nature and all the fields we've cooked up, to Lush, maybe they're just labels we slap on the weirdness of special relativity plus classical kinematics when you're really strict about it.
There's something almost philosophical there, right? Like, is a force always a force? Or sometimes just the universe's way of bookkeeping as things zoom around with Einstein's rules?
For sure. And sometimes I wonder, like, if you could go back and tell Faraday or Maxwell, hey, what you thought was a core force of nature might just be a perspective effect if you're riding along with the particles, would they be delighted or horrified?
Ha!
Ever wondered how magnetic forces emerge from the subtle dance of relativistic motion? Discover how Thomas precession transforms standard Coulomb forces into intriguing magnetic effects. By delving into Leonard-Vichet potentials and Lorentz force derivations, we see charged particles' motions laid bare. Relativistic kinematics underpin these subtle electromagnetic interactions. Observing from a moving test particle's frame reveals no conventional Coriolis force, only its antithesis. Thomas precession generates effective pseudo-forces, challenging our expectations of inertial frames. Detailed analysis shows that the anti-Coriolis force matches the magnetic force. Mathematical equivalence emerges when mass factors cancel, confirming a deep connection between motion and magnetism. When anticentrifugal forces overcome Coulomb repulsion at femtometer scales, theory hints at parallels with the strong force. This surprising derivation bridges electromagnetism and nuclear binding. In mutual circular motion, derivations converge. Concluding remarks show Thomas' precession not only explains magnetic effects, but may illuminate the strong forces underlying nature.
The paper we're diving into today is Composite Photon Energy Frequency Relation, revised 6 February 2019, and it's by David Lush. I have to say, this was not your standard run-of-the-mill quantum mechanics paper.
No, not at all. I mean, just from the title, you know you're in for some fundamental questions about what a photon actually is. Honestly, when I first saw it, I thought, okay, another tweak on E equals Vovac. But it goes way deeper than that.
Exactly. So the core question that Lush is tackling is, does the energy of a photon really have to be E equals h nu, that is, Planck's constant times the frequency? Or, if we imagine the photon as a composite, meaning made up of two tiny, oppositely charged, spinning particles, does that change the relationship in a meaningful way?
Yeah, and this is pretty significant because, well, you and I grew up with the idea that the photon is this indivisible quantum of light, massless, just pure energy zipping through the void. But Lush asks, what if that's actually not the whole story? What if photons actually have a little internal structure? If true, it could change how we think about blackbody radiation, quantum mechanics, all of it.
So maybe let's explain for a sec what he means by massive composite photon. This is not what most physicists believe. Normally, photons are considered elementary and massless. But Lush says, imagine a photon as two classical charges, like tiny, oppositely charged particles, spinning around each other at nearly the speed of light.
And then he uses this setup to try to explain the energy-frequency relationship of photons. Turns out, it almost hits Planck's E equals h nu, but not quite. According to his calculations, the energy is actually closer to h nu divided by 2, that is, E equals h nu over 2.
Exactly. And he says this factor of half isn't just a random mistake or some technicality. It actually emerges from the way the electromagnetic field would oscillate thanks to this spinning motion and from the relativistic Doppler effect, which, by the way, is the same effect that makes stars appear red or blue when they're moving toward or away from us, depending on the frequency shift.
And this is where it gets interesting. Lush points out that, in this composite model, the photon energy comes out to h nu over 2, regardless of the mass or charge of its supposed constituents. And he connects this to Planck's blackbody spectrum, the classic formula about the spectrum of light emitted by a hot object.
Yeah, he argues that Planck's original theory assumed standing wave modes, which don't have momentum. Photons, on the other hand, do. So, Lush suggests, maybe each energy quantum that Planck described is really made up of two photons, each carrying only half the energy we traditionally assign them.
That's wild, right? It kind of flips the standard quantum picture on its head. So, in Lush's view, the photon isn't the basic quantum of electromagnetic field energy, it's sort of half a quantum, so to speak, and you need two to make a Planck quantum.
Right. So what does he do with all this? Well, he applies it to a couple of big quantum puzzles. One is the so-called spin-orbit coupling anomaly, where the energy differences in atomic spectral lines are off by a factor of 2 from what classical models would predict.
Yeah, and physicists normally patch that up with something called Thomas precession, which is this relativistic effect you see in spinning particles. But Lush says, look, if you accept this halved photon energy, you don't need a complex precession effect to fix the math. You just get the right number straightforwardly.
Honestly, I see the appeal of a simpler solution, but I'm not sure this composite photon model would work with everything we know about quantum electrodynamics, or even about photons themselves not having mass. I mean, experiments consistently suggest the photon's mass is vanishingly small, if not zero.
I get that. And Lush kind of admits that his approach is speculative, a new way of framing old issues. He does tie it back into the historical development, like how de Broglie first imagined wave-like matter and struggled with frequency relations. There's an almost poetic symmetry in reversing that logic for photons themselves.
Can I digress for a sec? I once read that someone tried to define a massive photon to explain why you sometimes get light bending a bit more than expected in plasma. But the results never quite lined up, and you end up with limits on photon mass that are so tiny they're kind of mind-boggling.
That's a great tangent.